Okay, thank you, Marina, for your introduction. And yes, second and last lecture of me today, no more third part. So let's perhaps recall a little bit where we were ending last time. So we had Riemann surface. Then we had a map M into some symmetric space. So that was the example I've taken. So this is symmetric space. Symmetric space. And this was a harmonic map. So then we have explained how this harmonic map induces, well, I don't write everything down, but gives a family of flat connections, and I write them out. So there was some E plus lambda inverse D, and then it was plus lambda E, and then complex conjugate, where we discussed that complex conjugate, depending on whether this is a compact symmetric space or a non-compact symmetric space, will have different effects. So usually you should think of this as minus conjugate transposed on a matrix or just conjugate transposed. So let's here perhaps for being more explicit. So this is usually, so phi bar, I should say it's like minus phi dagger means, adjoint. And in the compact case, so for GK compact, well, I'm cheating here in the sense that I then assume that the group G is sort of sits in unitary group, right? And then I can do things like that. So then it's really just adjoint, or it's this for GK not compact. So this is an example, and we gave two examples yesterday, and you should keep these two examples in mind. One was Grassmannian, and the other one was the space of Hermitian metrics on Cn, I believe, one example of volume 1, or the space of Euclidean metrics on Rn of volume 1, which I think Charles then used in his second talk. So this is kind of what you should think of. So that this is flat for all lambda in S1, and the S1 that lambda has unit length is just to make sure that these conditions here so if lambda would not have unit length, then you would destroy, of course, this, and then it becomes a complex connection. So, and we have seen in Mike Wolf's talk yesterday, he was actually trying to scale exactly that parameter, or some parameter related to that parameter to infinity when he scaled out his cubic differential. So this is flat for all lambda in S1. So where this is this K connection, so this was a K connection. And so if G is compact and K is a subgroup, then that's usually a unitary connection. So this whole thing will be a unitary connection for the compact symmetric space. And this guy was, of course, lived in this P bundle, right? So lived this one form with values in P. One form with values in P. So this was what we ended up yesterday. Now, there were a few questions which I should answer. One question was, so I claimed so what the other thing we did was for later purposes, it is useful to move away from the unit circle and let lambda be a complex number also. And then, of course, these become complex connections. But that's fine, so I will not write this out today, but we did that yesterday. So some questions was, when I claimed, well, if I produce such families of connections by some method, right? I haven't told you which method, then I have a harmonic map. And we know, of course, that phi is related to the del derivative of my harmonic map. So when we come from this side, having a map, moving over here, then this is what we get. But how do you go back, right? So the question is, if I give you such a connection, how do you make the harmonic map? So that was a question I got from a number of people. So I will briefly explain that. Yesterday, didn't have enough time to do that. So this is fairly simple. So I already mentioned some important property. If you have any flat connection anywhere on some bundle or on some principal bundle, it doesn't matter. Then it's only invariant it has is its monodromy, right? So it is wise, hence, to look at the monodromy of this connection. So I choose a base point on my Riemann surface M and look at the monodromy representation of this connection, say, into the group, of course, we'll go into the group G. The whole thing is a G connection. So this is the monodromy, or holonomy, the same for me, of d lambda. So holonomy representation, rep of d lambda. The flat connections has a monodromy representation for a fixed base point in M. So if we get this question came yesterday, if we have a map, a harmonic map on this Riemann surface M, then we know that if I put lambda equals 1, or if I'd rigged it differently, I could choose any point on the unit circle, but for us, lambda equals 1 was kind of special, then this connection is trivial. That means that the monodromy is trivial at lambda equals to 1, if I want to reconstruct a harmonic map. So it's a necessary condition on this surface M. So we know that the lambda equals 1 is a trivial representation. And here is probably the remark which will also be where you see the difference between compact and non-compact symmetric spaces. So far, I haven't said anything about what that Riemann surface should be, or this could be, for instance, the complex line. Like in Mike Wolf's talk, he started out the complex line. That's a non-compact symmetric Riemann surface. So clearly, you will have harmonic maps into non-compact symmetric spaces. But my interest, or of many people's interest, is M is a compact Riemann surface. So now assume M is a compact Riemann surface, then from basic maximum principle argument, you know there cannot be a harmonic map of a compact Riemann surface in these negatively curved or non-compact symmetric spaces. So that means this condition that my connection is trivial at some point on the unit circle can never be fulfilled, right? So you will, for the in the case of non-compact target symmetric space, this is not the case. So you will definitely have a representation at lambda equals to 1, right? So I should probably mention that never the case if G mod K is not compact, the non-compact case. So in this, of course, the non-compact case is what we will hear probably more about in Subojoy's talk also, and we have in Mike Wolf's talk seen this. So this is this then relates to higher Teichmüller theory and non-abelian Hodge theory. So this is typically this case. Then you will at lambda equals 1 have a representation, so right? And what we want to show is somehow explain is if I reconstruct from this loop the harmonic map, then this harmonic map will of course be equivariant with respect to that representation, with respect to the back transformations on M and that representation acting by isometries on the symmetric space. So, okay, but for if we have a compact if we want to have compact surfaces and we are in the case of harmonic maps into compact symmetric spaces, this is a condition we can have. And it's an important condition because that ensures that the image is in fact a compact Riemann surface. It's a compact set inside that symmetric space. And that's what we want in that case of compact targets. Take the three sphere, the famous examples of minimal compact surfaces in the three sphere. So, of course, so this was now a little detour, which maybe is not, which we will, of course, aware of, but what can I do? I can now find, since this is a flat connection on the universal cover, it can be gauged to the trivial connection. So I can gauge. So call it F. Many people call it F, which maps universal. I should probably F lambda, which maps the universal cover of M into G for each lambda in S1. So I am, and that has the property that D lambda is gauged. So this dot means gauged by F lambda is the trivial connection D. So I'm gauging the flat connection on the universal cover. I can always do that. So if the domain manifold is simply connected, every flat connection can be gauged to the trivial connection. So I have this. So what this gives me is a map F lambda. For each lambda, I now have this map into the group, and now I project this map. So what property does the map have? Well, clearly this map is constructed. So if I take an element in the deck transformations and pull this back, I get exactly rho lambda times F lambda. So this map F lambda has exactly monodromy, if you like, as a map into the group by my monodromy representation of my connection. That's almost a circular argument, because that's exactly what it means. What monodromy is defined by this formula, essentially. So gamma, of course, is an element in the, if you like, fundamental group acting by deck transformations on my surface. Okay, so now I'm projecting F lambda down to the symmetric space. So now I define F sub lambda, which goes from the universal cover into G mod K. And I let F lambda, of course, be simply the coset. So it's a bit perverse written, but I don't know. I don't want to use pi, because I use pi later for projections between branched coverings and so on. So I can maybe write like this. If you are unhappy, this means at each point, this is an element in the group, and that's the, the stabilizer group. So this is an element in the symmetric space. I could also write class of F, of capital F lambda. So now, if you did the exercise, if you would maybe you see this, if you are not super familiar with this, then if I had started with this particular map in my construction, then the connection I would have produced is this one. So that means these F lambdas are all harmonic maps, right? Also harmonic maps. And so this is usually called the associated family of harmonic maps. You get a whole loop of harmonic maps parameterized over the unit circle. And this is the associated family of harmonic maps. And of course, this you have seen in your first differential geometry class. If you think of a minimal surface in R3, then a standard example is the catenoid. And then you know very well the catenoid has a deformation through minimal surfaces into the helicoid. And that's exactly this. So, and I will show you for constant mean curvature, I will show you a few little videos and pictures sort of in about 5 minutes. And then you will see another example of this associated family of harmonic maps. So this, in the case when the target Riemann surface symmetric space is compact, this is a quite important geometric interpretation of this loop of flat connection. You might say, well, this is sort of an algebraic, you built here something, and what's the meaning? Well, the meaning is exactly this helicoid goes to catenoid. So there's a geometry in this. Okay, so, but now you notice that this condition here, which I have elaborated on, so I get this. This means that at lambda equals to 1, this guy, so F lambda, of course, a harmonic map, but it's equivariant, so I should write this down by construction with respect to rho lambda, right? That comes from this condition here, but for in the case when the connection is really trivial at lambda equals to 1, then if I plug lambda equals to 1 in this harmonic circle of harmonic maps, right, this family, then I get a map from the compact Riemann surface or whatever, or from whatever the quotient is under the fundamental group. So this means here continue. So if rho lambda equal rho at lambda equals to 1 is the trivial, that means that I have really F at lambda equals to 1, which is, of course, is a map goes down to the Riemann surface. So I have a G, so this is sort of the reverse construction which I sort of implicitly assumed yesterday, and it's not clear whether everybody has thought through these thoughts, but this is how you do it. So that's why I claim having such families of connection is it. So once you have that, you do have your harmonic map. You don't have to do anything else anymore. It's not like you have to sort of, you might think, oh my God, this only encodes the derivative of the map, and so I have to do an extra integration. Of course, there is one extra integration, this equation, right? But that's an ODE. How do we find the gauge between a flat connection to trivial connection? So that is an ODE you have to solve, but once you have done this and you have sort of control over its monodromy and so on, you do get a harmonic map living on the actual surface under that condition. And remember yesterday, I said this is an important condition. They call it the closing condition, period closing. That's what classical geometers call that. And there were a bunch of other conditions, which I'm not going to repeat, just in words, that the residue of this connection at lambda equals to 0 has to be a 1-0 form, namely the phi, the Higgs field, the del derivative of the map. And then it was the symmetric space was encoded also by knowing that if I move from lambda to minus lambda, the connection gets gauged by the symmetry of the symmetric space, or the symmetry which defines the symmetric space. So this is a nice view so that you have packaged the whole geometry or the whole setup into this connection and its properties. But this is kind of the idea here. Okay, so this explains how to go back. And so now we have this equivalence, right, between these families and harmonic maps. And as I said before, this condition if the target is a non-compact symmetric space will never hold. So we will have at lambda equals to 1 also a representation. And that representation is then the, with respect to which your map is equivalent. Yes, you have a question. Yes? Oh, if M is a compact Riemann surface, there are no harmonic maps into non-compact symmetric spaces. Imagine a hyperbolic 3 space, right, as a target. There are no compact minimal surfaces in hyperbolic 3 space. So that's it. So where is I used to have notes because today I should be better organized than yesterday, because yesterday my 3-year-old woke up at 4 a.m. So, I was like, it's 6 hours, 5 hours of sleep, but I seem to have functioned. Today he slept a long time and I'm not functioning. So that's the kind of problem here. Okay, so I see where to go now. So you see here, this representations here. So lambda is in S1. This is the focus, of course, because in some sense the representations will, in all cases, give you at least the gauge class of your flat connection. So that's an important thing to study. Now, this is typically mathematics. You say, aha, I have a map from a domain into something, and it's a family of maps, so I can move that family parameter into the target, right? And that gives you the loop group. So now let's define lambda g to be all maps little g, and here there's a matter of taste, so I start really on the punctured C, or later you could write here S1 if you wanted, right? That's also good, but now I have to write, if it's really defined here, I have to write into the complexification. It has the property that if I evaluate at 1 over lambda bar, I get g of lambda bar, right? So you have to have this condition, and that just ensures that if I restrict the unit circle, I live in G. So this ensures that the image of G of the unit circle is contained in the real Lie group. It's just a reality condition. You could, of course, if I immediately define, so another way to say is take G on S1, real analytic, say, into the real group, and then extend it, to C star or have punctured C. But this is the loop group, right? And this loop group sits, of course, in the complexified, so I write GC. So these are just the maps which don't have the reality condition, or the unitarity condition, however you want to call that. So just maps like this, right? So they don't have this condition, so you don't know here that on the unit circle you end up in the real group. This is called the loop group, right? It's very simple, it's clear, it's called the loop groups, nothing deep about this. And with that loop group, we can view our problem here of our connection. So we can now write rho lambda as a, so at first this sounds like just a what you call it, a pointless categorical redefinition. And later on, perhaps this is a little bit more helpful. So this will now be a map into the loop, a representation in the loop group. So I still keep the lambda here to indicate, I should, of course, if I were a true mathematician, erase the lambda because the lambda is now coming on here. But just for future clarity, I think it's still cool to keep the lambda here. Just remember, this is now a map into the loop group, this representation. So we have so you can think of it, we have a loop connection, loop algebra valued algebra connection. And that guy induces flat, of course. And that makes a flat, makes a loop group valued representation, right? I bundled them all together. Hey, so we have that. So now this was a remark we need. And now I can start out with some rough complexity discussion. So, and I do want to present this, even so it takes time away, but it gives you an idea, perhaps historically, why this problem took, perhaps now in the 1970s, people started doing these sort of things, and maybe now it's 50 years later, and it took really a while to understand this, where the issues are. So let's do some kind of, there's a trichotomy. I don't know how to spell this, so I write trichotomy. And the trichotomy is modeled, of course, on the compact Riemann surface, right? So the first case is the genus of M is 0. So the non-abelian Hodge people, of course, are not interested in that because Higgs bundles not stable, blah, blah, blah. So it's not a good case. Everything is trivial. So we don't want to study this. But for the compact target spaces, it's an important case. You want to know all minimal two spheres in S5, S9, S7, Sn, in CPN, Grossmannians, wherever you are in compact Riemannian symmetric space, you understand these two spheres. So for genus M equals 0, the situation is actually quite nice. What happens is that this map, so first of all, the representation rho lambda is trivial for all lambda because you are on a simply connected domain. So there is no, there's nothing. So it's just, and what that means is that map F lambda I have constructed does live on M. So M is now like the two sphere and maps into, so where does now F lambda map? You see, I can either view F lambda as a map like I've done with my representation into G, or I can think of it as a map into the loop group. So this map goes into the loop group of G. I have here line, I don't know. Did I do the line? Probably. And for all lambda in S1, you have this map, and then you could extend it to lambda in C star, then you get a map into the complexified loop group. And so there's now a famous theorem by Uhlenbeck, mid-80s, and Siegel has redone this later. Presley and Siegel wrote a book called Loop Groups. And using this setup, which Uhlenbeck didn't have, so this is all about, so Uhlenbeck's definitely around 1985, roughly, I'm not sure, maybe 84. And Siegel is a bit later, maybe 1990. I'm not totally sure about this, but they have proven the following, that this map takes image in the polynomial loop group. So just polynomials, right? So F lambda of M, where M is the genus 0, is contained in the polynomial loops. Polynomial loop group of G. So this means if you look at the loops, they're just polynomials in lambda. And that is the famous unitone decomposition, which Uhlenbeck proved, and then Siegel reproved by this theorem here, decomposition. Now this theorem here relies a bit on the fact that you have to study kind of this loop group. You have to, in my case, or in the case of a symmetric space, you would have to factor out that K, because the constant loops, they should go sort of are not, you factor them out, and then this becomes some Kähler, infinite dimensional Kähler space. And so you use some algebraic geometry in there to prove that you really stay in some finite dimensional strata. That's how Siegel proves that. Moreover, the energy of the harmonic map you have constructed, right? So let's take the energy of F is a degree, not the degree of the polynomial, but the degree with respect to the Kähler form on this thing. So it's degree of the map capital F lambda. So, right. So that's what I should say here. Right. So this lives in the polynomial loops for each lambda. Sorry. So now I have to be. So you see, now I'm digging my own grave. F lambda is really one map because it goes into the loop group, right? So this is a map, and I should say it like this, and then you get and F is F is really the guy which you make at lambda equals to 1. So I should say, so this would be again the projection at F. And I should perhaps also, there's much more detail I don't really want to get into because that's a case which has been well studied. And this leads to this, what other people will call super minimal maps, totally isotropic maps. The first person studied it was Calabi for target space, the n-sphere. Later on, people did a CPN that was 2 physicists whose name I forgot. Then it was Eels and Wood, then it was Burstel and Wood, and so on and so on. There's a huge slew of long literature where this case is studied, but at the end of the day, it's this. Right? And then you can refine this for particular symmetric spaces and prove lots of things, which people have done over time. So in this sense, this is the trivial case, right? So completely understood. So you can essentially compute all these things. There's a paper by Jörn Wolfson for the Grassmannian, where you have these augmentations of sub-bundle, holomorphic bundles, and so forth. So this leads a little bit into algebraic geometry, but you can do all that, right? So this is purely complex variable theory. It's like minimal surfaces, right? Just holomorphic data, rational holomorphic data, I should say. So maybe the keyword here is, so all obtained by rational data. This is very vague, right? By rational data, I mean holomorphic stuff on the two-sphere. Rational data. So the next case, so of course, the second case where people really struggled is when the genus is 1. So I'm building up, and it's exactly the trichotomy you do for Riemann surfaces. Genus 0, genus 1, and then the rest. So genus M equals 1, so this is a torus. So M is some torus, and the torus is R2 or C, hence modulo some period lattice. Right, so this is standard picture we have. This is gamma, and the quotient is my torus. Then I'm looking at my monodromy representation. Rho lambda is then given by 2 commuting matrices. Okay, so maybe gamma, of course, is abelian. It's a Z2. And so rho lambda is given by 2 commuting elements, call it R1, R2. Where do they live? They live in the loop group of this group G. Because every representation you have, and if this is just Z2, then it's given by 2 commuting matrices. Just need to specify 2 commuting matrices, representation is there. Okay, so remember I said before, in order to do a little bit more, utilize complex variables and so on, you do want the lambda to be in punctured C, and then really you can think of this as living in the complexified GC, loops in GC, but they have a reality condition, right? With so these R1s, they depend on lambda, so I put this in here. They are lambda dependent because they live in the loop group, right? So with the property that, of course, R1 of lambda and Rk of lambda is in S1, is in the real group for lambda in S1. So we will see this is a good condition, or at least we need to encode this somehow, otherwise you're not getting back the representation into the real group. So what so now think about linear algebra. So when I give you two commuting matrices, what things are really invariant on those? And what object, you've learned the linear algebra. What is it? The eigenspaces, right? The same eigenspace. Okay, so that means, now drawing just a picture in order to not spend too much time. So here's C star, this is where lambda lives. And then I pick one of these two commuting matrices, and I generically, well, matrices, they live in some Lie group, but I'm from now on assume the Lie group lives in some GLN, right? So it's a matrix Lie group, or it's kind of subgroup. So every compact group, of course, has that, but I work only with if you have a representation to some matrix group. So then you have an n by n matrix, which depends on the parameter lambda, and generically it decomposes into n many eigenlines, right? So for generic lambda, so I choose here a particular point, lambda, then over it you have exactly n many eigenlines. N many. I draw them like this, eigenlines, right? Generic lambda. But then, as we well know, I mean, there might be some values of lambda where the matrix doesn't decompose into eigenlines, has some Jordan decomposition and so forth. And what that, of course, entails is that if I follow this, I will see branching, right? I mean, maybe branching here. It could be even worse branch. I mean, it doesn't need to branch like this. Could go out here. Maybe all three come together. So this means eigenlines starting to coincide, right? Then you go out again, go out again, go out again. Maybe these come together, and then you go out again, go out again. So I hope it's clear. And so this continues on the right side. So what you get is an n-fold branched cover, right, of punctured C. So this is an n-fold branched cover. N-fold branched cover of C without the origin. So it's not C dual C, it just means punctured C. And you see here special points, these branch points. The red guys, so these are the branch points. Branch values, I should say. And the guy upstairs is the branch points. Right? Branch points, branch values. So you get this degree n map down. So this is a Riemann surface up there, right? This Riemann surface is constructed from a harmonic map from a two torus into the symmetric space. So now you have an auxiliary Riemann surface of possibly very high genus, but unfortunately a non-compact one because 0 and infinity are missing. But there's a non-so-trivial theorem. So this goes back to, I think in this setup, definitely Hitchin, but then in sort of a different mode. I mean, in this generalized setup, I think nobody has ever written down the proof, but people, this is what it should be. But I presume there's a theorem, right? So Hitchin, Pinker-Stirling. I just give some references. There's, of course, depending on what cases you study, what symmetric space you have in mind. So Hitchin did it for the symmetric space S3. Pinker and Stirling for, I think, symmetric space was S2, the normal maps of Gauss, of CMC surfaces, and then you can build this up. There's a bunch of papers which study this. So the important theorem is this Riemann surface, the green Riemann surface extends into 0 and infinity. So the ellipticity of the harmonic map equations, ellipticity of harmonic map equation, this is a subtle argument. Equation implies that this green surface here, which I call, let's call that sigma, green surface, which goes down to C, punctured C, extends into over P1, so where lambda is in P1, right? And so I put a bar over it, but I delete it immediately. I don't want to schlep a bar around. So sigma is now a compact Riemann surface. This becomes now a compact Riemann surface. And degree n branched over P1, where lambda is in P1. And it has a real involution. The real involution comes from the fact, which I mentioned here, that this matrix I use to define this, and you see this doesn't depend which matrix I choose, because this picture, they're commuting matrices, I could choose any of the two. If I choose R1, the R2 gives the same Riemann surface. And so the real involution comes from the fact that if lambda, so covering lambda goes to 1 over lambda bar. So this comes from my reality condition. So
Franz?
Yes, generating.
Can you say a word about why you get the same Riemann surface if you choose R1 or if you choose R2?
Well, commuting matrices have the same eigenspaces. So if it's an eigenline for R1, it's an eigenline for R2, and vice versa. Right? It's linear algebra. It's not deep. So, as long as you stay on eigenlines and not start doing characteristic polynomials, then you could of course parameterize eigenlines by the characteristic polynomials of the matrix, the eigenvalues, then they change when I take different matrices, but not the lines. Okay, so this is a beautiful picture, and let me find, so I have not cheated at all here, but I have dropped a little bit of information. Namely, what have I sort of got lost in this whole discussion? So when I do this, this perhaps be too much detail. Let's get to that later. So do not cross. Okay, do not cross. I come over here. So what I'm going to do with this, right? So I have this, I have associated to my harmonic map from a torus, this high genus, possibly high genus Riemann surface, which is depending on what groups I have, what my representation of my abstract group was in some matrix group, n-fold cover. And now I want to do something, I want to be very aware that what are the points on my Riemann surface? A point on this Riemann surface is a line, an eigenline for this matrix which depends on lambda. So if I fix lambda, then I get the eigenlines on top. So what that means is at each point on the Riemann surface, I have given a line inside Cn, the n-time matrix. That defines a line bundle over my surface, right? So since little l in sigma is a line inside Cn, right? I obtain a line bundle L over sigma is a holomorphic line bundle. Now, those who know about holomorphic line bundles a bit, so it's called the Picard group of some fixed degree d degree of sigma. So it's an element in this Picard group, but as you all know, not know, I should tell you, the Picard group is C times C to the power genus of sigma modulo a period lattice lambda, where the lambda is, of course, a C to the 2G. So the fixed degree, so this line bundle, some fixed degree, this Picard, in this Picard torus is that. So now I come to my remark. This whole construction had a base point. The base point at which I computed my holonomy or my monodromy. So everything from here on is base point dependent. So in this picture, so for instance, these matrices are base point dependent because they are the representation. So that means, in principle, the sigma is base point dependent, but then you can show if you move from one base point to the other, you do a parallel transport on your bundle, and that gives an isomorphism of Riemann surfaces. But what doesn't quite work is that line bundle I have constructed that has the base point in it. So I have here this line bundle, and I should encode that it has a base point attached. This is a point in the torus. And now, of course, comes the big theorem, which is the linearization of the harmonic map equations in this case. And you can guess the theorem now, right? I already told you it's the linearization. So what can move linearly? Well, this is a torus. P2 is a torus. Well, so the map P, so if I move my base point around, I should move linearly in my Picard. So that's the big integrable system theorem. This is linearization. By linearization, I don't mean taking a derivative or anything. This is a complete linearization of the harmonic map equations as they are, not the linearization of the equations, right? So that means the map from T2 into fixed degree of sigma, where you map a bundle L with some point, a point P, or P naught I called it, goes to the bundle LP is linear. It's a group homomorphism, if you like. It's a fancy way to say it, group homomorphism. But it means that it's a linear map if you think of it. The torus is a complex line on R2, and the peak is some big torus, so it's a linear map. So this is the, so this is a really, really strong statement, because that tells you every harmonic map from a two torus into a compact symmetric space can be obtained from a linear flow on some fixed peak. You know, if you shift, then it's in the Jacobian. So could you switch this on? Then I want to show you. Yeah, that's good. Yes. So I wanted to show you that this is really non-trivial. So let's see. So it's technically a bit difficult because we have to switch. So let me do a couple of things. Yeah. So I should. Am I able to do this? How do I? How can I activate this so that it starts moving? If it's a video, what would I do? This is a video, hopefully. Yeah, it moves. Okay. So how did you do that? Oh, well, I can also click over here. Right? So, thanks. So what you see here are these Delaunay surfaces. So this is go back to, and you see the undaloids coming up, and well, the movie stopped. But you can see the famous undaloids by Delaunay, and if they, let me see whether it of course didn't do, I have to go back. Yeah, here they are. And this is this is a harmonic map into the two-sphere because it's a constant curvature in three space. And so this is the associated family of harmonic maps into the two-sphere, pictured on the CMC surfaces. So it interpolates between the nodoidal Delaunay surfaces and the undaloidal Delaunay surfaces, and in between are these screw motion invariant surfaces, which people call the Twistlers. So this was not demonstrating the theorem. This was demonstrating something I said at the very beginning, the associated family of harmonic maps, which I said catenoid goes to helicoid, but this is a slightly more interesting example. So now, if I'm right, I'm showing you now the picture of the last theorem. So here you have a genus 3 curve sigma, and sigma is called the spectral curve because if you do enough physics, then you understand it encodes the spectrum of some operator, which I don't. So they call it spectral curve. Here's the Jacobian. It's a three-dimensional Jacobian, or Picard. You have shifted it into the degree 0. And this is a correct picture because I told you there's a reality condition I have. And so my complex three-dimensional Jacobian becomes a real three-dimensional Jacobian. And in this real three-dimensional Jacobian, I have this linear flow. And here you see the linear flow is this plane, just a plane in this Jacobian, right? In these three torus. And you see I have cleverly placed it so that that plane is a lattice plane. That's exactly the condition that the resulting surface, that the constant mean curvature torus in this case, is closed. It's really a torus. That means this plane needs to be a lattice plane. So hit lattices, points, right? And so what you get is a famous example. It's called the spectral genus 3 constant mean curvature surface. It's the Dobrina torus. The reason is that Dobrina was a student of Klein, or perhaps a student of Klein, I don't know. And he had this surface written out on paper, coordinates. Had no idea that it closes, but it was a PhD problem. He was given by Klein. I think there's a slight refinement of this statement. And he computed it. So if Venti had known that, right? Wente didn't read further. Wente read what did he read? Eisenhardt, I think, or something. And Eisenhardt actually has a reference on that. And Wente stopped reading before the reference came. Then Wente went ahead and proved the Wente torus exists. But if Wente read another page, he would have found this guy and probably proven this guy exists, right? By elementary means, of course. So why is this a good example? Because, let me see, just go on. Here's another picture of it. So you see a wireframe picture. So this is a torus topologically. And here you see a nice animation, which I really like, which shows you how this torus is built. So you see essentially one set of curvature lines, and now the other set of curvature lines moves along the first set of curvature, the first curvature line, and sweeps out the Dobrina torus. So, right, now you see something which I haven't quite explained. There's a deformation of this thing. What's the deformation? I mean, I have a plane in a three-dimensional Jacobian. I can parallel translate that plane and it stays a lattice plane. So I get a one-parameter family of deformations, and all of these surfaces are constant in curvature. So this theory is really powerful because it completely defines, gives you all these surfaces or all harmonic maps and all their deformations and everything, right? And the cross sections, which you see here, are not so easy to understand. Maybe if you have looked at this, how this was built, I don't know whether I can show this again, but this way, maybe I show it again just for fun. You see that these are principal curvature lines. You see that they are always in a sphere. Watch, this curve you're seeing is always in a sphere or in a plane. So this is the defining, that separates the variable of this problem. You study these surfaces or special harmonic maps where you know certain things live in certain families of curvature lines or whatever live on spheres or planes, and then you get these special examples. So here's a more complicated guy, has higher genus. And so let me animate this guy. This is probably genus 5, I'm not completely sure. So you have many more deformations of this constant mean curvature torus because your Jacobian is 5-dimensional. The plane is 2-dimensional, so you have 2 or 3 dimensions. You can parallel transport that plane around, and that is the deformation you're seeing. And if you start looking at that, and you're familiar, for instance, with smoke ring flow and nonlinear Schrödinger theory, then you notice that Soul curve. You see, this guy looks like a curve on which these bubbles are arranged. So that Soul curve moves according to a first or second nonlinear Schrödinger flow, approximately. Nobody has ever proven anything like this, but these experiments show that, obviously. So people, once they've seen all that, then there's a lot of things you can simply do, right? So here's another nice deformation. You've seen the Wente torus, and on the show how the Wente torus are made. You've started with one of these Delaunay Twizzlers, and now you bend these Twizzlers, and you see now you have a Wente torus with many bubbles, and you can see down there counts the bubbles. On the left side, you see the spectral curve, you see the branch diagram. Here you see the conformal type of the torus produced. So 5 bubbles, 4 bubbles, 3 bubbles is the classical Wente torus. So you get them all for free now because you have this machinery. So here you see some other examples, the figure 8 torus. I want to point out again, it has a very thin conformal structure as you expect. I mean, the people who do Teichmüller theory see immediately this has to be something like this. The branch diagram of this curve sigma, and you can count what genus this have. Also, zero and infinity are branched, so you count the interior, gives you the genus. So 4, 5 probably, if I'm not right. So it's genus, spectral genus 5. And you can do anything you like here. See, bands, trefoil, and so forth. Okay, so stop here. So now I will move on to higher genus, and this is the examples you should have in mind. These are the famous Lawson examples, Lawson surfaces in S3, and there's genus 2, the genus 1 is just the Clifford torus, as you can intuit. It has just one hole. Oh, I have here a pointer, but I don't know how to use the pointer. Here. So these 2 holes are really the genus. So it's the same view. This is a stereo projection from the 3 sphere to R3. This is a different stereographic projection. So these surfaces in the 3 sphere, as Ulrich Pinkel has explained, are minimal, but projected into R3, they are Wilmore. But we like these big, S3 is hard to draw, right? So, and these black dots, which become a bit bigger here, they are artifact of the numerics, because here's a umbilic point, and the umbilic points are always hard to draw numerically or by. But anyway, so this is genus 2, 2, 3, 4, 5, genus 6. So of course it has a hat, just looks strange, but it should close like this. It's just not drawn. So these are the surfaces which Lawson made, and of course the objective in this whole picture was, once you have understood genus 1 so well, how do you do higher genus? Right? How do you get those? Okay, so is the person still here, or who can move this up? Maybe not, so I close this. Close. So maybe if he's not here, oh, it goes by itself. Fantastic. So I have 10 more minutes to explain. Sorry? Did I do something wrong? Did I do this? No, I did not do this, of course. Well, how would I do this, right? I fix it. What happened? Did I touch it and get electrocuted? Probably not. Right? So I wait for somebody to help me. Would be, of course, a good way to go. You give a lecture and die. So what better death could you have? Right? So. Yes, you can ask questions, of course, please. Another raise? Any questions? You have a question? Yeah, I mean, that's not so easy to explain in a short time. But what you can do, the gist of it is that such linear planes inside the Jacobian or Picasso are describable by theta functions. So can in principle write out theta function formulas for the thing. Another way to think of it is you can parameterize these line bundles by holomorphic sections and so forth, and then use those, evaluate at certain points the sections. That gives you an R3 if you do it right with the reality condition, and then you can kind of make out of this plane the total. So there's some kind of a little bit of a black box magic, so the viewpoint is this is the real object. The constant curvature guy or the harmonic guy in the two-sphere is its shadow. This is really the thing, right, which lives somewhere in an ideal Platonic universe. And then you have a technical construction, it's a construction from essentially Riemann surface theory, how to go back to R3. Not super well known, but theta functions is an answer and so forth. So there's explicit formulas. And the person to quote is Bobenko, obviously, who did that. Right? Okay, so I leave the loop groups up. So what happened to this now? Sorry? Shall I leave it like that, or? Sorry? Electrician will come. Good. So I. Sorry? Yes. Can I erase value? Okay. Yes. Which condition? That's not present on the harmonic. Yeah, the conformality on the harmonic map is that it's not conformal. The harmonic map into the two-sphere is not conformal. The Gauss map is not conformal. And from the Gauss map, I think, I don't show, maybe I didn't show this last time, but I did actually. I showed you if you have the Gauss map, you can reconstruct the CMC surface by one integration. And that is then a conformal map, obviously. Automatically, when you have to start from a non-conformal harmonic map into the two-sphere in order to get a CMC surface in R3. If the Gauss map were conformally, were holomorphic, and then you would have a minimal surface. So, so the theory is on the harmonic maps, not on the surfaces themselves. Okay. Does this answer that a little bit? Okay, so now, unfortunately, or fortunately for all of you, is the last bit. More chalk. So here, perhaps. Well, the trichotomy, right? So higher genus. What do we do? So what goes out the window immediately is this monodromy. This picture cannot hold. You don't have such commuting matrices and the eigenlines, so this fails. So people didn't know. This is where this kind of DPW stuff comes in, and that's the Iwasawa decomposition. 5 minutes. Of loop groups. And that's simply the following statement, that you take the loop group of, say, G is now a compact, He has to be a compact Lie group. This doesn't work for non-compact or not globally, G compact. And then you take, this group is isomorphic to the real loops times loops, which I call plus GC. So you need to know what that is. So these are maps, these are the loops G, which are defined on all of C into GC. Yeah, you can fix. Yeah. So please, you fix, I lecture. So this is called the positive group. So these loops, so this guy, remember that these guys here, they're just maps from punctured C into the complexified group. These are the loops which on the unit circle live in the compact Lie group loops, and these guys are the ones which extend holomorphically into 0 in that lambda parameter. This is the Iwasawa decomposition. So now an important thing to note is that if you take some of the connections we had, so D plus lambda inverse phi plus lambda phi bar, say, if you gauge them with this plus group, the only thing you get then this residue at 0, so the simple pole at 0, is preserved because the gauge extends in lambda to 0. So it cannot add any higher powers in the spectral parameter. So if I gauge d lambda by some g lambda, so that will be some new connection plus lambda inverse, and so g lambda now is in the plus group, and that will be a new select, and here you just have a conjugation. So here you get g lambda inverse or at g lambda, at g at lambda equals to 0, and I think it's inverse, unfortunately, inverse. That's because I gauge from the right, so this is, but that's all irrelevant, phi, plus, and then you get higher order terms, right? So then you would get lambda inverse, maybe you get another constant terms, they're all in the connection, and then you get a lambda times, call it mu1, plus lambda square, mu2, plus goes on further. So any gauge by a positive guy preserves the simple pole at lambda equals to 0, but the residue changes. Now the residue changes by conjugation by an element in my complex group G. So this is evaluated at lambda equals to 0, so this is just an element in the group. So what does that mean? Remember, phi is the del derivative of the harmonic map. If you have a higher rank symmetric space, you have lots of invariant polynomials. And since phi is a holomorphic object, all these polynomials give you differentials, holomorphic differentials. And those are preserved under gauging by the plus group. So that's really an important fact. So all invariant polynomials which give holomorphic differentials. If the rank is 1, there's only one, the killing form. You get a quadratic differential, but if the rank is high, you get different ones, holomorphic differentials. Are preserved under this gauge, are preserved under lambda plus GC gauge. This is almost, of course, a trivial observation, but an important observation. That means that everything you want to attach, like Mike Wolf called them conserved quantities on the harmonic map, they're preserved under this infinite dimensional gauge group. So here now see that since we're in a symmetric space, there's just more happening than if you just had an arbitrary Riemannian target. You have a huge symmetry group acting on your problem. And the theorem by DPW and maybe improvements over time is the following, that you can gauge so that what you get after gauge is a meromorphic connection, right? So there exists gauge G lambda on the surface M of now higher genus into the plus group so that d lambda h g lambda is meromorphic. So this is then looks like this. So maybe d tilde plus, then it has an inverse term. I write it mu minus 1 plus lambda mu 1 plus and so on is meromorphic on meromorphic. I.e., so I should tell you what that means. That means that the mu k's are meromorphic forms with values, well, you know, depending now whether I have a symmetric space or something more different, then they take values in the various p parts or eigenspaces of some high order automorphism in the Lie algebra. It doesn't matter. I just write here they are meromorphic forms with values just in maybe, let's be simple, SLNC, if I have a matrix group. So they are meromorphic one forms, and they all have the same pole divisor. There's only one, the pole divisor does not depend on lambda, so it's a fixed pole divisor where all these infinitely many meromorphic forms have poles. So pole divisor independent of K. Independent of K. So this is the Weierstrass representation, right? You get so that this is a meromorphic connection. So you might say, what's that good for? Well, you see, this is, of course, a statement because harmonic maps are into these symmetric spaces. The equations are nonlinear, but you have reduced the problem again, in some sense, to a linear problem, namely a meromorphic connection, right? So this is the Weierstrass theta, or generalized Weierstrass theta. Okay. So the proof, I have no time to explain, but it's very elementary. You write out the condition that this should be, has no 0-1 part. That's the condition. That gives you a del bar problem on this map. And in the sheaf of meromorphic functions, you can solve del bar problems. So that's about it. You have to endow these groups, they're infinite dimensional, with some Banach structure, whatever, and then you use some theorem that this all works also for Banach-Lie groups and so forth. So it's pretty straightforward to prove this. So now you can say, okay, where are we here? Well, we are somewhere in the 19th century, right? When Weierstrass and Co. and Riemann said, oh, all minimal surfaces come from holomorphic, meromorphic functions. And we have seen many lectures where this theme, you know, was used in very intelligent and highly sophisticated ways. And here's the same, except we are not in the 19th century, in the 21st century. Now you have to say, okay, let's start using this, right? Write down reasonable meromorphic data to make examples of harmonic maps. So the objective at this stage is, can you now use this to get high genus or higher genus harmonic maps? Right? Using that. Then you say, all right. So one thing I should perhaps mention here, since the original guy was a real connection, meaning, so for instance, if I'm in UN, it's a unitarizable connection. These guys are unitarizable or real also. So they have, after some gauge with the plus group, they must be unitary connections. So meromorphic and unitarizable. This, of course, not so clear. So if you think of it, if I give you, so these are, after all, still flat connections, everything. So if I write down the monodrome representation of this, and I ask you to tell me when is it a unitarizable representation? You shake your head, say no hope. If you have a high genus Riemann surface, how can you do this? So the fix here, or at least one idea which people have pursued in the last perhaps 5-6 years, is use symmetries on the Riemann surface. On Riemann surface M, so that the problem of first writing down meromorphic data and checking whether the representation of this connection is unitarizable is somehow doable. And as you saw Lawson surfaces, and so far, I think the only examples where this worked are 2 examples. I finished my talk here. So the first example is when the Riemann surface of genus, so this has some genus G, goes down to CP1, so some cover minus 3 points, which can be 0, 1, infinity, or 4 points, which can then be which are 1, plus minus 1, and plus minus I. I could this slightly more general. Here there's no, these points can just, they are, because 3 points have no invariant. All conformal classes are the same. But these here, they are, as you know, they have cross ratio -1 actually, and you could perhaps move this to, so this is a square here, and you could perhaps refine this to a rectangle, so, but all real cross ratio. So you might say, what is he doing now? Where does this go to? So what I mean is, this compact Riemann surface has a branched cover where these 3 points on CP1 are the branch values, and then there are branch points up here. And likewise has 4 branch values, and then has branch points in the compact Riemann surface upstairs. And then what you do is, you run this whole machine downstairs and pull it up. And so when you do this, you have to deal with meromorphic connections on a triply punctured sphere. And people know this. These are Fuchsian equations, for instance. These are examples. So let me, here you could use Fuchsian connections, Fuchsian meromorphic connections, Fuchsian connections, so which have poles only in these 3 or 4 points. And this is about the only cases which have been studied. And they give you, so I write here 1, and now 1 is of course erasable because I have given essentially all the cases which have been studied, I have written in one blackboard. So this gives you Fuchsian connections. So what that means is that if you write down such a guy over here, so let's call that perhaps D hat. So if I write down such a D hat, then it looks exactly as you imagine. It has some residue matrix, and then it's Z over Z plus, so in this case up here. Then another residue matrix, Z minus 1, and then at infinity it's determined. And then plus, say, D trivial connection, if I work on some trivial CN bundle. So this is a Fuchsian connection. Residues at infinity, there's residues minus A1, minus A2. And these, of course, depend on lambda. So they don't depend on Z, they're only lambda dependent to get a connection in this loop group, and that's it. And now you study these, and there's good conditions when such objects are unitarizable. When you have, so this is so people call log connections, whatever, you know when you can unitarize them monodromically. And that's what is used in these, right? Because there's a reasonably good theory, if the Lie group is not too complicated, again, to describe the character variety of thrice or quadruply punctured spheres. And if you, the unitarizability locus in there. And if you know the unitarizability locus, you have a chance to prove existence of such residues which actually unitarize the representation. And then it's easy to prove that's essentially the reverse of TPW. Then there is such a gauge which moves you back to a connection of this type, and then you have your harmonic map. And you can also, as you notice by this invariance under this gauge group of the invariant polynomial holomorphic differentials, you already have a good, at least a partial understanding of the geometry of the map, that for instance, for minimal surfaces, CMC or whatever, the holomorphic, the quadratic Hopf differential is preserved. So that you know it from get-go, you know what the Hopf differential is when you start here. That's built, has to be built in the Weierstrass data. Right, and so
Franz, we should
stop.
Or maybe wrap up.
I am done. So the only thing I want to say, there are 2 examples, which are the ones I showed you, the Lawson family and generalizations. And then Charles might talk about minimal Lagrangians in CP2. So these are the only examples so far known using this theory. So high genus. Okay, sorry, I went a bit over time, actually. Not too much, but
No, not too much, not too much.
Not worse than Mike Wolf.
So thank you very much.
Sorry.
And I'm sure you have questions for Franz.
Ben has one.
I had a question. So if you want the harmonic maps also to be minimal, does that have a nice meaning in this?
Yes, it has, because as I said, I mean, maybe you missed that, but
Yeah, you probably said, sorry.
yeah, but it's fine. So because we write down this Weierstrass data here, then the mu minus 1 or its conjugacy class defines the Hopf differential. So if this guy is nilpotent, for instance, depending on what your conformality condition is, then you would have conformality. So conformality you can easily read off from the Weierstrass data. What you cannot read off is the induced metric, for instance, if you care for that. That's a much more tricky problem because it's kind of hidden, because you're doing sort of this reverse gauge. Right? You're using this decomposition essentially to go back. But the conformality can be checked. It's built in, actually.
I see. And similarly in genus 1 and genus 0, I guess?
In genus 0, they are always conformal.
Oh, yeah, I guess.
In genus 1, they are also built in that spectral curve. Namely, if you have a branching over 0 and infinity, it's conformal. If it's not branched, it's not conformal. It's not easy to see. But there's an explicit condition. You remember at the spectral curve, at the sigma over P1, and if you are not branched over, if you're totally branched over 0 and infinity, so everything, all sheets collapse there, then you're talking about a conformal harmonic map. In genus 1.
So these are special cases of constrained Wilmore surfaces?
Which ones?
Or the scenario you described today, constrained Wilmore surfaces? Are they special cases of constrained Wilmore surfaces? I was asking.
Let me try to understand your question. So which examples? Do you mean on the tori or on the higher genus?
Theory, isn't it?
Oh, harmonic map theory, of course. Constrained Wilmore surfaces are constrained harmonic maps. Constrained harmonic maps.
Just Wilmore surfaces.
But just Wilmore surfaces are harmonic maps. Not the surfaces themselves, but the Gauss maps.
The Gauss maps, okay.
Right, so and for a Wilmore surface, the correct Gauss map is not what you think, because the Wilmore problem is Möbius invariant in the target. So you attach to each point on your surface a two-sphere. You attach the two-sphere, which happens to have the same mean curvature than the surface at that point. Oh, okay. It's called the central, whatever it's called, the mean curvature two-sphere. So each point does not have a tangent plane, which the regular Gauss map or the normal plane. You attach these two spheres at each point, which touch, of course, they're tangent and have the same mean curvature. So it's a higher order contact, right? The mean curvature is second order. So you have these two spheres on your surface, and when you do a Möbius transformation, that goes correctly. So this is a Möbius invariant construction, and the space of two spheres is a four-dimensional sphere inside Lorentz 5 space. Okay. You know, Lorentz 5 space, you take the sphere, the unit sphere in Lorentz 5 space. It's this cooling tower, looking hyperboloid. One sheeted four-dimensional thing, and points on there are spheres in R3, right? And so this map from the domain into this four-dimensional sphere in Lorentz space is in fact minimal.
It's minimal.
It's minimal. It's conformal harmonic, and it fails and has branching along the umbilic points of the original surface. And the problem here is that it's no longer true branch points are isolated. You could have whole curves of branching. There are examples. But yes, it's a harmonic map, unfortunately, into a, what do you call it, pseudo-Riemannian symmetric space, right? Or whatever you call these things, right? For which you can do these things, but not like this global decomposition is no longer the case. And there are papers by Dorfmeister and some of his students who actually study what happens for these Lorentz groups when G is not like a compact Lie group like SON or SUN.
Do you still get flat connections?
Oh, yes, everything else is fine. The whole setup works. What doesn't work, of course, is these very detailed constructions at the end.
Okay. Thank you.
Or hasn't been done. I don't say it doesn't work, but hasn't really been done. But look up Dorfmeister's papers. There's a whole slew of papers where he even does the Wilmore case, very detailed.
More questions?